Okay, 2.C.4. Somebody read it to me. 2.C.4.
The studio student.
Wow. Sure you're Jackie.
Electron bond stars and predicts molecular geometry, Lewis diagrams, and the VSEPR model.
The VSEPR model, yes. How many people all remember Lewis diagrams? Kinda. Okay. So we are going to do a quick review of how to draw a Lewis diagram, or a Lewis structure, or a Lewis dot structure. What's the first step?
Draw the atoms.
Count the number of valence electrons.
Nice. Somebody used a word that is very important. We don't just count the electrons, we count the valence electrons. What are the 3 ways of knowing how many valence electrons an atom has?
Counting on the periodic table.
Counting from left to right on the periodic table. Column 1 has 1 valence electrons. Column 2 has 2 valence electrons. Skip the D block. The next column, the boron group, has 3 valence electrons. 4, 5, 6, 7, and 8 valence electrons. What's another way of knowing? Electron configuration. If I'm doing phosphorus, for example, I could represent it. Well, I can do the full one. Phosphorus, 1s2, 2s2, 2p6, 3s2, 3p3. Which ones are valence? The ones that are in the highest numbered subshells. So the 3s and the 3p, 2 here, 3 here, that's a total of 5 valence electrons. Wait, Michael.
Would that thing change when you get further into the table where there's different number F's and D's and then that's
So we get to something like let's do actually arsenic. Arsenic, I'm going to shortcut it and do argon. And then it's 4s2, 3d10, 4p3. So what I said was just pick the ones with the highest numbers. So that's why we ignore the D's, because they're actually in the lower energy level. Technically the 4s and the 4p are the valence ones for arsenic. So this has 5, which makes sense because it's the same column as phosphorus and nitrogen, which would also be 5.
So you'd forego the F block too then?
Yeah, F block is always going to be a lower number than the other subshells that are in there as well. Okay? The last way is to just memorize every single atom. It's a terrible way to do it. Okay, so either use the periodic table or electron configurations to help you count the number of valence electrons. So, an example. I want to do the sulfite ion. SO3 2-. So we're going to count them. Sulfur has 6. Oxygen 6, and there's 3 of those. So that gives me 24.
Plus 2.
But it's a -2 charge. So I'm going to add 2 more, take into account the charge, and we get 26 total electrons. Those are O's. Sulfur, maybe I should say sulfur equals 6, oxygen equals 6, oxygen equals 6.
Okay.
Those are the number of valence electrons they have. Okay. Step 2.
Draw them out.
Draw them out, connect them. Oh, okay.
Nah. You gotta
have these.
You gotta do it in a pretty looking way.
Everything has to have octets.
I can make octets with that.
Use parallel electrons to form bonds. Well, if it's not like
So usually for what we're going to have to do, we'll talk about a few exceptions to this where we're drawing longer sort of carbon chain molecules, but usually for most of these things, we're just going to pick one atom to go in the middle. Pick a central atom and draw a line to each of the other ones. That represents a bond. Pick a central. How do we know who's going to go in the middle?
the different one. The one that we have in one.
Usually it's the one we have only one of. It's usually the one that's first in the formula. But there is actually some rules. We go by lowest valence, because it's going to need to make the most bonds to complete its valence shell. Now, sulfur and oxygen all have the same number of valence electrons, so there's another rule that usually it goes the one with the lower electronegativity. Okay, but yeah, in general, it's the one that there's only one of. We're not going to put oxygen in the middle, put sulfur on the outside. We'll pick the one that there's only one of, and put that one in the middle, pick the central atom, and make one bond with each other atom. We're not going to get fancy and try to draw some weird snaky thing like that for a simple molecule like this. We're just going to put sulfur in the middle, and we're going to connect each of the oxygens with a bond. How do we draw a bond? With a line. But what does the line represent? Represents 2 electrons being shared between these atoms. So really, you got to think about these as a pair of electrons. Okay. Step 3.
You count,
Put the rest of the valence electrons.
Put in the rest of the electrons
try to get octet rule.
and try to, not necessarily octet, try to fill the valence shell, which means for hydrogen we're trying to get a duet, right? Not a niet. A duet. 2 electrons in hydrogen. Why does hydrogen only need 2?
Because it's very, very small. Doesn't have a P. Only has an S.
It only has 1 subshell in the first energy level, the 1s. There's no such thing as a 1p, so it only needs to fill the 1s, which only holds 2 electrons. Nice. So we're going to fill in the rest. Now, what's going to make it easiest if you fill in the rest starting on the outside. To complete the valence shells. So I'm going to put octet or duet. How many did I draw so far?
6.
6. 2, 4, 6. Each of these lines represents 2. So here's 8. Here's 10, here's 12. We put them in pairs, because 2 electrons fit into an orbital, right? These things are still going to live in orbitals, all right? And so usually by convention 2, we put them top, bottom, left, and right. So 2 shared here, they count for sulfur and they count for oxygen. So oxygen's got 2, 4, 6, 8. It's filled its outer shell. It's good to go. Let's move over to this other oxygen. Hold on, I lost count. 12, okay. 14, 16, 18, that one's good. Move to this one, 20, 22, 24, sulfur. 26. Cool.
Wait, what about like the exception ones?
What about the
Aren't there like some of them that hold like 10 or something?
Yes, there are some molecules that exceed the octet. But there are rules for who can exceed the octet.
So there's no like.
Actually, any element in row 3 or below can exceed the octet. Why? Why is it only row 3 and below that can exceed the octet?
Got more shit on subshells.
They have, well, do they have a D? Does phosphorus have a D?
Oh, row 3 and below. Okay. Oh, well, it has the potential to have it.
It has an empty D subshell there, right? When we get into the third shell, 3s3p, there's an empty 3d subshell there as well. It's not filled normally in phosphorus, but if I need to put electrons in there, I can put them in there. So So phosphorus can go above the octet because it can put any extra electrons into its empty 3D subshell. Can nitrogen do that? No. Why not?
It's a weak link.
Well, it's got an infinite number of shells.
It doesn't have a D subshell.
It doesn't have another D subshell in the second shell. There's no such thing as a 2D, right? All right, so we should maybe add something here. Extras go on central atom. And I'll put third row or below only on there. When I publish this one to YouTube, feel free to load up the comments with who's the clown in front playing with the green balloon.
It's fun.
Oh, I'm sure it is. It's not distracting at all. You're listening, right? It's all about you. Okay. SO3 was not actually the example I wanted to do. Sorry, sulfite was not the example I wanted to do. I wanted to do just sulfur trioxide. So here we're going to have 24 electrons. So, pick our central atom. It's still going to be sulfur. Make one bond to each. Start filling them in. 2, 4, 6 already shown. Here's 8, 10, 12, 14, 16, 18, 20, 22, 24. Stop! Don't you dare put that other dot down there. Why not?
You've exceeded the limit.
We're out of electrons. We only had 24 electrons to work with. I've represented 24 electrons here. I don't just put 2 more because I got to fill everybody's valence shell.
Are we gonna make the map?
These inanimate objects must be happy. Now we get to step 4. What's step 4?
Make additional
Use
bonds.
the
Make
extra
additional
bonding pairs.
Make additional bonds if needed. Yes. There's actually no way that I can really push around. I can't just give this pair to sulfur because then oxygen's not going to be satisfying its octet. I almost said atom. Okay. So if I can't just move them around,
You double them.
I can take one of those that I just gave to an oxygen and I can share it. The sulfur says, come on, oxygen. Come on, man. I just need 2 more. Can't you just share some more? Sure. Boom. Make another bond. Get rid of them there. Because the bonding pair counts for both atoms, this oxygen has 2, 4, 6, 8 electrons around it. This sulfur has 2, 4, 6, 8 electrons around it. Question? Yes. Why did I choose the oxygen on the left?
Because you wanted to.
Because I wanted to. No. Because I wasn't done yet. In reality, I could have made that double bond with the oxygen on top. I also could have made that double bond with the oxygen to the right. Which of these is correct?
Doesn't matter.
The one
It's
you
all
did.
about a perspective. You just gotta look at it, turn your head a little bit. They're all the same. Yeah, you gotta look at the angles.
That's, we're getting there eventually. The reason we're trying to draw these Lewis structures so we can figure out what shape the molecule is, and then once we know the shape, we can figure out whether the molecule is balanced or unbalanced in terms of its distribution of electrons, whether it's polar or non-polar. This was a trick question.
They're all right.
None of them is right
Or no.
by itself.
So you have to draw all of them?
It's only correct if we draw all of them, because in reality, the molecule exists somewhere in between these three structures.
They're all the same.
Now, what I mean by that, hold on, what I mean by that is sometimes confusing, because sometimes you'll see little double arrows here. What does the double arrow imply?
Any of
They're
these.
switching.
Double arrow implies that it's moving back and forth between these different forms, like somehow this double bond is jumping from atom to atom. That is not actually true. In reality, the molecule is an average of all of these. These are what we call resonance structures. The term resonance structure is misleading in and of itself, because resonance implies motion, moving back and forth. In reality, the molecule is an average of all three of these. What do I mean by that? Well, this bond is a double bond here, a single bond here, and a single bond here.
What is it then?
On average, it's about 4/3 of a bond. It's a little bit stronger than a single bond, but quite a bit weaker than a double bond.
So could you draw it for me?
So there are pictures that you might see for this molecule where they will draw something like this. No. No, you're not there yet. When you take organic chemistry, maybe they'll let you get away with it.
Yeah, but who wants to take a
Chemists.
Yeah.
Nerds, yeah. Future nerds. Gluttons for punishment. But that picture on the upper right is a little bit better of a picture, because in reality, two things are going to happen. One, if I measure this molecule, well, how could I measure it?
An experimental data.
What kind of experimental data?
Infrared
Infrared spectroscopy! Yes. If this bond was really a double bond, and this bond was a single bond, then we might see two separate dips in the IR spectra, right?
Yes.
Because the double bond vibrates more quickly than a single bond, right?
Dance party.
Yeah, dance party. Okay, but in reality, we would only see one dip, meaning that all those three bonds are actually the same strength. Okay, there are other ways of measuring the bond energy. How much energy does it take to break that bond? And if we do that for SO3, we don't see two different energies that it takes to break these bonds. We only see one energy. So in reality, those bonds are actually somewhere in between a single and a double.
What happens to the valence electron?
What happens to the valence electrons?
That structure.
When we talk about hybridization, it might make more sense. When we talk about molecular orbitals, it might make a little bit more sense as well. Okay, but we're not quite there yet. We're getting there. It's in this section. All right. So step 4 is really what? Move lone pairs into shared pairs or bonding pairs. To make double or triple bonds. And then you're probably not going to be able to see this. Some of you that are over there, there's some balloons in the way, but at the very bottom I'm putting, don't forget resonance.
Gotcha.
Don't forget resonance. If there are multiple atoms that you could make that double or triple bond with, you got to show them all. I'll just take those just to avoid temptation.
Oh, nothing going on.
That's agreed. It's my lone pair, buddy.
I don't enjoy stapling myself, so you say.
Okay. You have to draw all possibilities to show the people that you understand that none of those structures is really correct all by itself. Resonance are all the possibilities. These are the 3 resonance structures of sulfur trioxide. In reality, it's not changing between those. It's an average, but unless you learn how to do it this way, which I don't think they're going to accept this necessarily on the AP exam.
What do we have like oxidant A? Do we have to
You won't have to. The most you would have to draw is maybe 4 possibilities. Okay, now, there's something we also have to understand that's called formal charge. Formal charge. Formal charge is a way of drawing multiple competing Lewis structures that both follow all the rules of Lewis structures, but to tell which one is better. For example, somebody might draw the Lewis structure for SO3 like this.
Well, yeah.
Why is it wrong? Does it have 24 electrons?
Yeah.
2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We're good.
Sulfur as well.
Sulfur is not obeying the octet rule, but it can exceed the octet rule because it is in the third period or below.
So what can it go to? Can it go like
Probably you won't have to. So who's better? Well, in reality, we'd have to do some experiments and try to figure out what is the actual strength of this bond. Are they double bonds? Are they as strong as other SO double bonds that we've seen before? Or is it closer to a single bond? Which might lead us to think about this. But there's a way of trying to predict which one is better. It's called formal charge. Formal charge is almost like saying if we were to break apart this molecule and split up all these bonding pairs, how many electrons would each element end up with? And then if we compare that to how many it had when it wasn't bonded, how many it brought into the molecule to begin with, that's going to give us an indication of what its sort of charge is. It's not really a charge, because in a charge, we're assuming that the electron got transferred from one atom to another. But this is like sort of, almost like a measure of how well did this atom come out in the bonding deal. If it brought in 6 electrons, does it still sort of have 6 electrons around it in the bonding? Well, no, they're all trying to get 8, right? But in calculating a formal charge, we're going to split up the bonding pairs. So the way we calculate formal charge is this. We take the number of valence electrons that it had originally, and we subtract how many it has in the Lewis structure. Now the rules are we take half the number of bonding electrons, and we take all of the lone pair electrons. Because the lone pair electrons only belong to one particular atom and not the others. So let's compare one of the resonance structures for SO3 from this solution we had on the left, and then we'll compare this proposed structure. Okay, let's start with this oxygen right here. How many valence electrons did it bring into the molecule? 6, right? It had 6 to begin with. Oxygen normally has 6 valence electrons. Now, in this Lewis structure, how many does it have? Well, it has 1 bonding pair, right? So it's going to get half of those, half of the 2 electrons that it's sharing with sulfur. And how many lone pair electrons does it have? 6. Half of 2 is 1, plus 6 is 7. 6 minus 7 is -1. So it's almost like oxygen has an extra electron around it in this structure compared to what it had in the neutral atom. So its formal charge, it's not really a charge, but its formal charge we say is -1. If we look at the oxygen up here, it's in the exact same situation. It has the same number of bonding pairs and lone pairs, so this formal charge is also going to be -1. How about the oxygen over here? You brought in 6. We're going to take away 2, or sorry, half of the bonding electrons, which it has 4 of those, and it has 4 lone pair electrons. So half of 4 is 2, plus the 4 lone pair electrons is 6. 6 minus 6 is 0. So the formal charge of oxygen here is 0. It has the same basic number of electrons it had that it brought in if we split those bonding ones up. How about sulfur? It also brought in 6. It has 8 bonding electrons, so we'll take half of those. It has no lone pair electrons. Half of 8 is 4. 6 minus 4 is
2.
plus 2. So that sulfur is almost like it's in a plus 2 state, because it brought in 6, but it had to share so many of those. Didn't really get a fair sharing, because if we split up those bonding ones, it's like it only has 4 now.
Do we add all the charges?
Now, one thing about formal charges, if you add them all up, it has to give you the charge of the molecule. So plus 2, -1, and 0 gives us a formal charge total of 0, which is good because this is a neutral molecule. If I did it for the sulfite ion that we drew before, it has to give us a total of -2. It has to equal the charge on the molecule. What about in this structure? What's the formal charge here? 0. It's exact same as the one we had on the left side. So all these are 0. So we know by the rule that I just said, if the sum is 0 and all the other ones are 0, sulfur has to be 0, but let's calculate it. It brought in 6. It has 2, 4, 6, 8, 10, 12 bonding electrons, which it's going to get half of, and it has no lone pair electrons. So 6 minus half of 12, 6 minus 6, 0. This is actually a better structure, because it has minimized the formal charges. Formal charges are as close to 0 as possible. They are all 0. Some structures you're not going to be able to get all zeros because you might have an overall charge. Okay? But the rule for formal charge is if you're comparing two structures, whichever structure gives you the overall formal charges that are all as small as possible, closest to 0 as possible, is the best structure. So they might ask you to draw SO3, and you might have to draw this, and you might have to draw your 3 resonance structures, and then they'll say, oh, well, look at this structure. How does this one compare to your structure based on formal charges? Based on formal charges, this is better, because they're all formal charge of 0, which is what we're trying to get. Okay. Will you ever be asked to come up with a structure like this? Absolutely not. You're going to follow these steps and you're going to draw this and its resonance structures, okay? But what it asks you to do in this little thing is it says, formal charges can be used as a criterion for determining which of several possible Lewis diagrams provides the best model. So if they give you multiple Lewis structures, you should be able to assign formal charges and decide which one is the best. The one that's the best gives you formal charges all closest to 0. Question?
So in this case, both of them, like the outside is equal to 0. Like, would it ever happen that like one of them would be 0?
Wait, say that again?
So in this case, like that was 0, 0, 0, 0, and then this one was -1, -1, and then 2. So like, would it ever end to that equals 0, 2? So will it ever happen that like the sum of it would be 0?
Yes. This is from last period. We did SO4 2 minus. If I assign formal charges here, all these oxygens on the outside are just like the 2 on the right for this structure, so they're all -1s. The sulfur in the middle here, it brought in 6, now it only gets 4, so it's a +2. When we add them together, plus 2, minus 1, minus 1, minus 1, minus 1, gives you the charge of the molecule. They have to add up to the charge of the species. SO3 was neutral, that's why it added to 0. Yes, there's a better structure than this.
Hey Nicholas. No, honestly, like last time it was like a minute.
Hold on. Chapter 8